and I'm very glad to introduce Professor Vivek Polshettiwar, who is Associate Professor at TIFR in Department of Chemical Sciences, Mumbai. And in one line, I could actually state his caliber by stating that he is one of India's finest exemplary researcher at his age, very young and very dynamic and very great achievements, which I'm going to actually elaborate as we move on. But he's one of an exemplary scientist that India could actually be proud of in area of nanocatalyst. Vivek works in a very specialized area of nanomaterials, nanocatalyst for energy and environment and protection, and with a greater selectivity. I only know difference between Vivek in catalyst is homogeneous catalyst and heterogeneous catalyst. Probably you'll have to teach us more than that today. Professor Polshettiwar, Vivek has actually citations which are very high numbers, 12,000, more than 12,000. H index is very great, 54. I hope Google Scholar updates that with his publication, recent publication in March 2020, which most of the researchers dream of. And I congratulate Vivek here today for your latest publication in PNS. I don't know how you do it from India, but it's a proud to know that you have a PNS paper, and it's every researcher's dream to publish at least one paper in PNS, and I hope you have many more over there. Vivek has done PhD in chemistry in 2005, DRD Gwalior, that's Madhya Pradesh. He did his postdocs and other stints at variety of international tenurships, including France. And he also went to Cincinnati for a long term, 2007 to 2009. He again went back to France as a visiting researcher. 2009 and 13, he became assistant professor. But I would like to mention here that for great reason, Vivek has actually preferred to be back to India. And I don't think that he would have achieved more than what he's achieving currently in TIFR. So I hope he doesn't miss US or France or other countries. He has many awards, and want to mention that he's a young career. He received a young career research award from Department of Science Technology by Government of India. He is also a member of fellow of Maharashtra Academy of Sciences. He's fellow of chemistry from India. He missed, or he preferred not to join Humboldt in 2009, but he was offered an Humboldt Alexander von Humboldt Stiftung Fellowship, and probably in future he would not be a postdoc fellow, but maybe a great experienced researcher fellow over there, which I will have little pride to say that we also come from the same Stiftung. So Vivek, it's great pleasure today on Saturday. Thank you coming on the board. I see you in the office or at home, and thank you for your time today. And let me introduce about audience. We are about 95 just now, and with this number, I think we'll strike probably close to 100. And it's great privilege to see you actually, and we met maybe 7-8 years back when maybe Dr. Venki Ramakrishnan was in TFR. That's a long time, and I hope that we'll meet soon post lockdown, either in Pune or Mumbai. So great pleasure. Over to you, Vivek. We welcome you.
Thank you very much, Jayant, for such an extensive introduction. And I also like to thank Satish for the invitation. As Jayant told you all, that I am a material scientist, and we design a new material ideally for a catalysis to take on the challenges of climate change and global warming. But since the audience is also mainly from a pharmaceutical colleges or a pharmaceutical background, the way I will definitely explain more about the nanomaterials. I will start my talk with the nanomaterials, why one has to use the nanomaterials. Then I will also explain the chemistry of climate change, the science behind the climate change, because I think every single human being need to understand the climate change, because then everyone can contribute to tackle the climate change. Afterwards, I'm going to use some of the results that we did in our lab, that we're carrying out in our lab to tackle the climate change. And at the end, I'm going to explain, I'm going to present some of the details of the nanomaterials that can be used in health, say to protect from the viruses, bacteria, for the drug delivery. So this is the way I'm going today. So why nano? Why do I need to use a nanomaterial? Why can't I just use the normal materials? So if one look at the nanomaterials, this nano is just a scale, right? It's nano equals to 10 to minus 9 meter. It's just a scale. Somehow, when you go to that scale, you start getting a better results. You start getting interesting results. The material dramatically change their properties when you go to the nanoscale. The typical definition of nanoscale is say 1 to 100 nanometer, a material which has 1 to 100 nanometer, but this is not really a perfect definition. You can have a nanomaterial with a 200 nanometer size showing nanoscale properties. You can even have a material with a 1000 nanometer size showing dramatic different properties than the bulk material. Sorry. And when you use a nanomaterial to develop different technologies, you call them a nanotechnology. To get a feeling of the scale, if you look at if you were to measure the length of a human, it will be billions of nanometers. And if you go to bottom of the scale, which is the atoms, let us say, then you ideally need if you align a 10 hydrogen atom parallelly, then you get a 1 nanometer. So it's really small scale. Now the question is why, when you go at such a nanoscale, why they show unusual property? What is the reason? So one of the simple reason is the surface area, surface to volume ratio. We know any material is made up of two things, right? You have a surface and then you have a bulk. When you are at a bulk, when you see the material around you, like say sand or something, or any material, you have a very small amount of surface as compared to the bulk material, right? But when you go to a nanoscale, for example, if you take a water drop, it has 100,000 molecule inside the bulk per one surface molecule. So you can see number of surface molecule is really small as compared to the bulk molecule. So the property of that drop is ideally because of the bulk molecules and not the surface molecules. But what will happen if I make all the molecules, I bring them on the surface? Something like this, you know, the coin. It's a 2 mm coin, it has a 2 surface layer and huge number of internal layers. If I divide that 2 mm into 1 mm, then you have a 2 surface layer for 5,100 internal layers. So by simply changing the size, you can increase number of surface layers. When you increase number of surface layers, ideally you are increasing number of atoms on the surfaces, right? And most of the activities, whether it's a pharmaceutical activity, whether it's a catalytic activity, light harvesting property, all of these is actually interaction of those molecules or photons with the surface atoms. So if I have more atoms on the surface, obviously they will show better activity. So that's the one reason I have more surface area, more atoms. And since the atoms are on the surface, you can see the atoms which are on the surface, they are only connected to atom in the second layer, right? There is no connection about top layer. So that means the coordination number of that atom is less as compared to the atoms in the bulk. So when the coordination number is less, the atoms are more energetic, they are more reactive. So you have more number of surface atoms and they are very reactive. And that causes the nanoparticle to behave dramatically different when as compared to a bulk material. For example, we know bulk gold is yellow, shiny yellow color. Why? Because it's a metallic. So it has an electron cloud. So that electron cloud is moving around the surface. When light comes, it deflects most of the light, except some portion of the blue light, and that's why it's yellow in color. So now the same gold, when you take that to a smaller scale, say 2 nanometer, 10 nanometer, 100 nanometer, the electron cloud of that gold, which was ideally reflecting the light, now start resonating with light. And when it resonates, it absorbs certain wavelength of the light, and that's why you get a different colors of the gold. So you can change the electronic properties of the material by simply changing the size of the particle. That's the reason for nanoparticle to show a different behavior dependence of the size. Another one is a melting point, right? Ideally, melting point is what? Converting solid into liquid, moving away those atoms a bit so that they become more mobile and become a liquid. So it's the energy required for these atoms to move away, right? That's a melting point. That's the energy. That's the definition of melting point. But if you look at the melting point of the gold again, it melts around 1064 degrees Celsius. So if it is the same gold, they should not really change the melting point, right? Because it's energy required to move the atoms. But now when you go to a nano gold, the melting point of the 2.5 nanometer size gold is 300 degrees Celsius. A dramatic decrease in the melting point. Now again, answer is the same. The atoms, see here, the atoms at the surfaces, they are coordinated only with a 1, 2, and 3. The 3, that surface atom is coordinated with the 3 atom, whereas the surface atoms in the bulk is coordinated with the 7 atoms. What it means is if I have to move this surface atom, I have to break only 3 bonds. So I need energy to break or lose these, lengthen these 3 bonds, right? Whereas if I have to move the atoms in the bulk, I have to break around seven interactions. So obviously, I need lesser energy to move these surface atoms, right? And that's why, and if you have more and more number of surface atoms, that means overall energy that is required to melt the material is less. So whenever you change the particle size, you reduce the melting point, obviously at a nanoscale. So, and there are several other properties that you change. You change the band gap, you change the energy of the electrons, you change the valence band, conduction band levels, you change the electronic properties, you change the mechanical properties, you change the light harvesting property when you change the size of the particle, simply changing the size of the particle. Obviously, there's a further development where you can also change the shape and morphology that allows you to do nanoparticles. And that's why it's a very unique material as compared to any other material that is known to us. Now the question is, how do I design such a small nanoparticle? Because they are so small, how do I design it? So there are two ways of making the nanoparticles. One is called a top-down method. So as word suggests, it's let us say if you want to make a gold nanoparticle, take your gold ring that you wear, some of you wear, and break it into smaller particles, right? And go up to nanoscale. Obviously, you can imagine now how do I really break that such a big particle into so small nanoparticles? They're 10 times the atoms, less than. So atom is 10 times more than the. So you need 10 atoms to make a 1 nanoparticle, right? It's really small. But there are instruments which allows you to break down these the bulk material into smaller nanoparticles. But obviously, there is a issue with the control over the particle size, their distribution, and shape. So most of the time, people don't use the top-down method. But there are some applications where you can use top-down method. Other one is the bottom-up, which is generally used. So what, again, the name suggests, bottom-up means what is at the bottom? Bottom is atoms and molecules. So I start with atoms and molecules and I force them to meet. And let us say I take 100 atoms of gold and I force them to meet and I get a nanoparticle made up of 100 atoms of gold. So maybe handling of the 100 atoms of the gold directly will not be feasible. So what one can take a gold salt, say HAUCl4 or AuCl3. It's like a sodium chloride. So some salt, you put it in the water and then you add some reducing agent. So the salt will become an atom. And then if you have a certain concentration of these atoms, then there is the energy of the system will be more, and then the atoms try to meet and form the crystals from the nanoparticles. So that's why by using atoms and molecules, you start making the gold nanoparticle or any nanoparticle. There you can control the size, shape, morphology, and different chemical properties of the material. That's why most of the time one use the bottom-up approach to make the nanoparticles. Right, so that is a very basic idea about the about the science behind the nanoparticles and why they show different activities. Now, the second part of my talk is about the climate change, and then I will come back to the nanoparticles and see how these nanoscience can help you to tackle the climate change. So, what is climate change? I guess most of you know is excess of greenhouse gases that causes the global warming, and once the temperature, there is a disturbance of the temperature in the environment, obviously that will affect the climate. So still, although all of you, I'm sure, knows it, still I really want to go into some of the basic science behind it so that you will really know what is happening. So one can look, this one particular slide can explain you the climate change very well. So it's called the Earth's energy budget. Now you can see our energy that we are getting is from the sun. So you get a good amount of energy from the sun, which is around 340.4 This is the unit, watt per meter square. It's a huge energy. Now, once that sun energy comes to Earth, what happened to it? Some of it, before reaching the surface, is absorbed by the atmosphere, right? We have the atmosphere made up of CO2 and other different gases. So some of these gases absorb these energy. And some portion of that is reached to the surface. And again, once it reaches to the surface, some portion of it gets absorbed and some portion of it gets reflected, right? So there is a light coming in and light getting reflected. But we also know that most of our body, when absorbs the light, they also emits the radiation. In several cases, IR radiation. So our surface, the planet Earth's surface, also emits lots of these radiation, lots of these lights. And then these energy ideally should go away from the Earth environment, but since we have the atmosphere made up of CO2 and different gases, some of these energy again get back to the Earth, and that's called the back radiation. And then lots of other energy. So in a simple thing, you have amount of energy coming in and amount of energy going away from the surface, from the planet, right? And that makes us that creates a livable environment on planet Earth with certain temperature that we need. But let us say if I stop letting these energy that is reflected or emitted by the surface going away from the atmosphere, from the planet Earth, and you keep capturing more and more of that energy which is supposed to go out, then what will happen? You will heat, right? You will heat the environment. And that's what exactly happening. Now the greenhouse gases, mainly CO2, is able to capture these radiations, mainly the IR radiation. And that's why you are trapping more and more heat, and that's how you are heating the environment, warming the globe. So what are the greenhouse gases? Mainly it's the CO2, which is the greenhouse gas. Methane is another one, nitrous oxide, and water vapor. Water vapor is also a greenhouse gas. Although there is some sort of a debate whether I should call water vapors as a greenhouse gas, because water vapors are produced in the environment because of the global warming by the other gases, methane, CO2. So as soon as you reduce the temperature, water vapor will go down, right? So I don't know whether one can really say the water vapor as a greenhouse gas, but it does cause the global warming, so one can. Now, where does this carbon dioxide and why they are greenhouse gases and why other molecules are not greenhouse gases? Answer is simple. What I said, the amount of energy that is going away is getting trapped. So what is that energy? Ideally, so the incoming energy is UV visible and some portion of the IR, but the outgoing energy, because of the thermal radiation of our surface and some reflection, is mainly infrared radiation. Now, so any molecule in the environment which absorbs the infrared radiation will cause a global warming, right? So that's the first condition, that molecule need to absorb the infrared radiation going away from the surface. And again, lifetime of that molecule, right? If there are large number of organic molecules absorb the infrared radiation, but you don't call them greenhouse gases because they are ideally not in a large quantity in the environment, and their lifetime is less because most of these can react with something and convert into something. But CO2 is highly unreactive. Methane is highly unreactive, so their lifetime is for years. They stay in the environment, right? So that's why these IR radiation harvester, those molecules which capture the IR radiation are greenhouse gases. Mainly then the CO2, obviously water vapor, some amount of ozone, methane, nitrous oxide. So ideally the CO2 is the main culprit. And why? Because most of our life is now become artificial. We need energy for every single thing, and we get most of this energy from fossil fuels. Now these are the carbon-based chemicals. So whenever you burn carbon-based chemical to get the energy, you get the CO2, right? And that's why the CO2 becomes the main cause of the global warming. So this is a cartoon again showing the same thing, that you produce lots of gases, creating the cloud of these gases, CO2. And now when sunlight comes in and sunlight has to go out, some amount get absorbed, some amount has to be reflected or radiated. That is not going away, and that's why the planet is heating, right? And now you can see the amount of CO2 that is increasing. So you can see up to 1950, the CO2 concentration in ppm was around say 280, 290 all the time. But suddenly at 1915, when you have this industrial the change in our lifetime, become more artificial, more energy dependent, you see a sudden increase in the now from 1960 to 2020. Now you can see we reach around 400 ppm, 415 ppm. That's the highest recorded in the human history. So that is a clear-cut indication that it's a CO2 which is causing the climate change. So what happens? The first thing is the global warming, the increase in the temperature. You can see now the temperature change. You can see there is a dramatic increase in the temperature change. I also showed you something called solar radiance in every average. But there are some people who don't believe that there is a global warming, and they say, okay, we're getting more energy from the sun, and that's why there's an increase in the warming. But you can see now, from say 1960 to this up to now, the amount of energy that amount of photons that you are getting from the sun is nearly the same, but the temperature is increasing. So that clearly indicates it's not the amount of energy that we achieve, but it is the amount of energy that we are trapping because of the excess of CO2 and other greenhouse gases. So what will happen if there is an increase in the temperature? You can see the Arctic Sea ice is melting. You can see with time now. This is the billions of kilometers, and you can see with time goes by, you can see the amount of ice is decreasing very dramatically, right? From 7 millions of kilometers to now we are around 3.5 millions of kilometers. So that's a dramatic decrease in the Arctic Sea. So what will happen if ice melts? Our sea levels will go up. There is something else that is also happen, and that is even more dangerous, and maybe the pharmaceutical students can need to solve this problem, which is, so there are diseases hidden in the ice, and they are waking up. Right, so I think now we are in this the one of the black time in the human history of the coronavirus. But if you look at the history of the human history, then we always existed side by side with bacteria and virus. There was always a bacteria and viruses, and somehow we evolved to resist them, and so we resisted them, and then viruses again evolved to resist themselves and infect us. So that's some sort of a battle that the human is going through from last several years. Even look at the coronavirus, this COVID-19. Before COVID-19, there was always we at least know there are several other families of the coronavirus. So there was some scientific knowledge about the coronavirus, and that could be the reason we're able to still able to fight at certain level to come up with the drugs and other possibilities. But let us imagine that the world is infected with a virus which is unknown to the scientists. We don't know anything about that. What will happen? What will happen? And so, however, what would happen if we suddenly exposed to a deadly bacteria or viruses that the human never seen for thousands of years? So that means there's no knowledge about that virus. We don't know the structure. We don't know how they act. So we can't really battle with them. And that is what is happening. Ideally, we don't really worry about the climate change. But look, in 2005, the NASA scientists revived a bacteria that is frozen in pond in Alaska, which is 32,000 years old. 2 years later, they came up with they discovered another bacterium which is 8 million year old in Antarctica, and there are large number of other discoveries where they start discovering lots of viruses. Why? Because now that ice is melting, right? Ice is melting very fast, and then those viruses which are in a dormant state now coming out. Very recent study in February 2017, NASA scientists announced that they found a 10 to 50,000 year old microbe inside the crystals of this Mexican mine. And these microbes have never seen the surface for over 4 million years. But once they removed it, they started reviving. They started multiplying. So they are still, so ideally they are there. They are living. They are not dead, right? They can live with different things, viruses, but still they are active. They are only in a dormant state. So if they come out, they start multiplying. And they observe that these bacteria have somehow become resistant to all to 18 types of antibiotics. All the top-notch antibiotic that we know, that particular bacteria was resistant to all of that. So you can imagine now if such a viruses and bacteria comes out because of the climate change, because of the melting of the ice, what will humans do, right? So best way is not to let them come out. And how do I do that? We have to stop the climate change. Somehow that's the most dangerous or most worrisome thing that the human is facing, even 1,000 times or million times more worrisome than the current coronavirus. Somehow we are not really that serious, because until something happened to us, we really don't be active, but you can see this is really dangerous. In addition to the health, what will happen if there is a global warming? The ocean will warm, right? The sea level will rise, and then the cities which are near the sea will impact first, and then when they migrate, entire world will impact. So there is a Nature Communication paper just last year, just few months before, where they showed that around 10 million, billions of people are now occupied land, which is less than 10 meters above the current height, and including 230 billions, which is about just 1 meter from the sea level. And now this is something of a artistic picture that is a gateway of India in Mumbai, and now you can see what will happen if there is a global warming. So that's really a serious issue, and one has to really stop the global warming. One has to really stop the climate change. Now the question is it too late to stop the climate change, or is there any way to stop the climate change? Obviously, there is no, I really don't know the answer, whether it is too late, but whatever it is, we should attempt it. We should attempt to resist it. We should attempt to stop it. Whether we succeed or not, that's something based on the science that we do, based on the fundamental discoveries that we the scientists will come up with to fight these climate change. So the one can say, oh, no, this is how the life is. Life is very complex, and now it's time for human to get extinct. That's one way of saying it and just enjoy. Another way is, no, we can fight back. We can solve the climate change problem. So obviously, there are two ways to solve the climate change problem. One is our societal responsibility, right? Minimizing the use of a carbon-based fuel, minimizing the use of artificial things, to be more nature-friendly, right? Some of these. In a science, at the science level, if I develop a technology which allows me to capture the CO2 and convert into something useful, say fuel, then it solves the problem ideally, right? It's the CO2 which is the main cause of the climate change. So if I can convert CO2 to something, some chemical, or say fuel, let us say you run your car using CNG, methane. So if I get a CO2, I think this that's the next, okay, maybe here. So this is the slide. So I know CO2 is my problem, CO2 is waste, but can I use that CO2 as my feedstock? Can I use that CO2 as a source for the chemical, source for the fuel? For example, can I drive my car by filling CO2? I fill the CO2 only once in my car and I drive my car for the lifetime. How do I do it? So look at the chemistry. So I have a CO2, you make a catalyst is a material which will have ability to capture the CO2, and I use the energy from the sunlight, capture the photon, and say water from the environment, and then I react CO2 with water using the sunlight, all three natural. CO2 is in excess, water is also there, and sunlight is also there, convert into methanol and methanol. And that's my fuel. CNG is nothing but a methanol, right? I burn methane, get the energy, I can drive my car or do some other work that you need the energy, right? And then once I burn the methane, I again get a CO2. But now I have a technology where I convert CO2 back to methane. So it's a cyclic process. No CO2 is going into the environment. No methane is going to the environment. We're just using the energy and only the water which is being used to convert CO2 to methane. Something like this. It looks like a dream, right? Can I drive a car by simply filling the CO2? But if you look at the science, it's still there. Science is already there. It's only about the productivity and how sustainably and economically you can do it. So I'm going to show you some of the examples that our lab has contributed in this particular field. So how do I now design these nanomaterials or these nanocatalysts which will have ability to capture the CO2 and convert it into fuel? So you need the way we do it, we have a 3-component system. We have a support, we have the active side, and we have something which will convert solar energy into hot electrons and heat. I will explain to you what I mean by that. So I can ideally just use a small nanoparticles, but if I use, because they are very active, but if I use a very small nanoparticle, then they try to come together. If I start with a 5 nanometer, they becomes 10, 20, 100, and activity goes down. So the stability is important, right? I don't want catalyst to die in a few hours. It should be stable for days and months and years, ideally. So what we do, we take that active site, that nanoparticles which does the catalyst, and fix onto some another bigger surface. Now, since we are fixing, they don't move, and if they don't move, they don't meet, and they don't grow into the size. So size remains the same, and there are several other advantages of using the support. So in our lab, we develop a support, which we call it as a fibrous silica. It's a silica, nanoscale size, having this dendritic fibrous morphology, and that's why this name, which allows you to tune the particle size. We can tune the particle size from 50 to 100, 100 to 200 based on the need. For a drug delivery application, you need a smaller particle so that they can penetrate into the cell. So there are possibility of designing those type of nanoparticles. It has high surface area. Even a 500 meters per gram is like if you take a 1 gram of this powder, you're going to have a 1 football ground surface area in 1 gram of a powder. That's really high amount of surface area. Then it has excellent thermal, hydrothermal, mechanical properties, and it's easy to synthesize. We recently came up with this Nature Protocol paper where we showed that any lab, even the lab in the colleges, the 12th and BSc can make this material. We have given the videos and total step-by recipe to really. Can you please mute the mic? ak.appsci. Can you please mute the mic? Thank you. So it's easy to synthesize. So no fancy technique is used, and that's very important. You don't want to just develop a nanomaterial which can be made in a milligram scale. You really want to make them in a large scale so that it can ideally, at the end of the day, can be used by the society for societal applications. So these are the SEM images showing that these are nanoparticles with some fibrous structures, and they are very monodispersed. These are the TM images again showing the monodispersed nature and the fibrous nature with a very unique pore size distribution by 5 nanometer to 5 nanometer. And we also try to understand in our lab why I got that fibrous sphere. Why not a rod or a rectangle or a solid sphere? Why that particular structure? So we try to understand this. So this may be a bit of higher, closer chemistry or deep chemistry, but still I want to show you how we make the material. So we start with a very small organic molecule. This CTAB that you some of you may be using as a micellar reagent, right? So this is the quaternary nitrogen and CH2CH2 16. So this has this tail and the head. So whenever you add these molecules into certain solvents, they try to self-assemble to minimize the total energy of the system. The polar head, non-polar tail, we added them into water and xylene, and they start self-assembling to minimize because if they are random, they have a total more surface or more energy. So they try to organize in the form of a lamellar phase. But there could be repulsion between these polar head groups. So we added one more co-surfactant, a pentanol in this case, and that reduces the repulsion and that stabilizes these interfaces. And what we also observe that these lamellar phases are not really floating into the solvent like a horizontal phases, but they are in the form of a spherical droplet. They are in the form of a bicontinuous microemulsion droplet. Bicontinuous because we're mixing xylene and water and emulsion droplet. So these droplets, which is ideally made up of just a CTAB, water, and xylene, these are not a nanoparticle. These are the template which makes the nanoparticles. These are some sort of a reactor. Now I can grow the silica inside these templates. And now we learn how to keep them away from each other. Then you get a smaller nanoparticle, or you can force them to merge together. And if that happens, you get a bigger size microemulsion droplet, and then you can grow a bigger size silica nanoparticles or some other nanoparticles. So that's how we make most of our nanoparticles. And allows you to tune the size, morphology, even number of these the fibers coming out from the surface. So our material, this is our own invented material, we have several patent and patent application, is now being used by more than 150 groups worldwide for a large number of applications: catalysis, fuel mitigation, drug delivery, sensing, energy harvesting. So I'm going to show you some examples of drug delivery once I finish with the climate change. So you can see this is one of the very few material that was invented by the Indian scientists. By most of the time, it's other way around. We try to copy Western world. So that's support. That's the only silica which really doesn't do a chemistry by itself. Obviously, we have recently showed some example, but in general, no, because it's a silica made of SiO2 with some OH on the surface. It doesn't have that much of chemistry on the surface. How do I make it active? So one of the way to make active, to convert, say, gives me the nickel, the CO2 cyclic chemistry. One of the simple way to make it active is take nanoparticles of say nickel, put it on a silica surface, and then that nickel shows a very good catalytic activity. But again, these particles try to oxidize. I need a nickel 0 to convert CO2. It goes on to oxidation, oxidized state of say +2, and you are not able to do a catalysis. So we had this challenge in our field. So what do I do now? If I replace nickel nanoparticles or nickel metal with any other metal, they will have same issue of the stability and oxidation and sintering. We thought of, can we develop a process where I don't want to use any nanoparticle and only silica should do the science, do the chemistry. And that's the paper that we recently came up in PNAS. There, what we thought of, this is a silica. I'm showing this silica, and this is how the silica surface looks like. Made up of SiO, just a random SiO network. Idea was, let me break this SiO bond and create some sort of a defect site. If I break homolytically, you have this O radical, the extra radical. If I break both the bond, then you will have this oxygen vacuum. We asked the question whether these radicals can activate the CO2. For that, we use the magnesiothermia technique. I'm not going to go into the details of that and try to create a defect site of a higher and higher concentration, 10, 25, 50. And here you see now, when we defected the material, you see that material start emitting different colors in UV light, indicating that those defects are color emitting defects. Then we tested that for this particular reaction. CO2 plus hydrogen gives me methane. Methane is my fuel, right? You can drive your car using methane. And we observed that yes, when you created a defect at 10, 25, 50, you started getting more and more methane. So we also observed that 25 is the best. Even after having more defect site, 50 is less active. So we try to answer those questions. We also study the stability of these materials, and we observe they are stable up to certain times, but they lose some activity. But then we showed that after every regeneration cycle, you keep increasing the catalytic activity. Since I have only 18 minutes left, I'm going to skip all of these more details of this particular project, and I'm going back to the third point. Now I have a support, I have active site, but I need energy, right? I showed you there we did the catalysis at 400 degrees Celsius. So that makes entire process non-sustainable. So now can I get energy from the sun, which is, and do the same chemistry? And that's the concept of called cold heating, where when I say I'm doing the reaction at 400 degrees Celsius, I heat entire reactor and do the reaction at 400 degrees Celsius. But if you look at the science, the chemistry is happening only at the surface. So I need 400 degrees Celsius only at the surface of the catalyst, not entire reactor. So that means, can I generate a heat 400 degrees Celsius only at the surface of the nanoparticle and keeping that reactor at room temperature? That's why the term called cool heating. Your reactor is cold, but surface is heated. How do I do it? So there is a concept called plasmonic resonance. This only happens when you are at a nanoscale, especially with gold, silver, copper in the visible light. So when you have these, let us say, gold nanoparticle, they have this electron cloud around. So when you expose that electron cloud with the sunlight, which has an electromagnetic field, then that electron cloud you see here start resonating with electric field, and that's the surface plasmon resonance. And by some mechanism, this resonance this particular resonance get damped, and that energy get absorbed by the nanoparticle, and that energy, the photon energy, then get converted either into the heat or into the hot electrons. The electron is in a higher excited state. So I can either use the heat or those hot electrons to carry out the reaction which I was carrying out at 400 degrees Celsius by thermal heating. So one of the things that we wanted to do is we wanted to make a gold nanoparticle such that they absorb entire solar light. Ideally, they absorb around 550 nanometer and some amount of other light. But we wanted such a flat absorption so that I can capture more and more sun photon to get more and more heat and more hot electrons. So we did that by tuning the two things. We tuned the nanoparticle sizes as well as the distance between the particles. The distance between the particle, how do I change the distance between the particle? That was the question that we asked. So ideally, I can change the size, shape, morphology of the nanoparticle. That's easy or well studied now. But how about the distances? So for distances, you see, this is the silica sheet. I functionalize the silica sheet with some organic group, and then I put one nanoparticle at each. And then I add another batch of gold salt. They will go and sit only onto the existing gold nanoparticle. Now you can see systematically increase the gold nanoparticle, you decrease the distances. There is a chemistry that is required to do that, which I'm not going into. But by doing that, you keep decreasing the distances between the gold particles. They are coming closer and closer. And when the particles come closer, the electron clouds start talking with each other, start interacting with each other, and that allows you to then absorb entire visible light. Now you can see these are the TM images indicating that yes, the gold particles are coming closer and closer with each other. And you can see now the gold, which is yellow when it is bulk, and when it is smaller nanoparticle, it's a reddish color or a reddish brown color. Now it becomes black. You get a black gold now. Gold is the same chemical state, same chemical composition, same oxidation state, no functionalization, no doping, but still black in color. By simply tuning the distances between the particle, they start resonating such that it absorbs entire visible and up to near IR light, and that black. And now, since it absorbs all of these photons, what will happen? You create either that, you convert either those photons into heat, so I get lots of heat, or I get those hot electrons that I can inject into the CO2 to convert into methane. So one of the things that we show, one can use this solar heating technique to convert seawater into desalination water. It's a desalination process where you convert seawater into potable water. You take a water with a seawater which having water molecules, H2O and salt, add the gold, black gold, expose with the sunlight. Black gold capture all of that sunlight and convert that into heat. You produce lots of heat. You evaporate the water, only the vapors, water vapors will go out and then condense. You get a pure water without any extra energy, just a solar heat, solar energy. Right, and then I skip this part. I have only 10 minutes remaining, and I can show you that we also did use this black gold to carry out simple alcohol oxidation reaction. And you can see now when the reaction is in dark, the conversion is around 20%. When you do it in the light, the conversion is 90%. No change in the temperature. We maintain the temperature, so it's a plasmonic behavior which polarizes the molecule. We increase the length of the bond, change the Bohr angle, makes that molecule really reactive to react, and that reduces the activation energy. I'm not going to details of the plasmonic catalyst, but that's how you can do a reaction at a room temperature with a far better activity. We also showed that one can react CO2 plus water to get methane using same black gold. You can see there is nothing else. Use water, CO2 to get a methane using sun, and the black gold is the only catalyst. It's not dying. You can keep using the black gold for a large number of times. So we also do other chemistry, like we developing material to only capture the CO2, but obviously the capturing is not the solution. You should capture and convert the CO2. Why do I use a nanoparticle? Still, nanoparticles, only surface atom is active. The other atom inside the nanoparticle is not really usable. So can I just use a single atom or atoms of 2-3 atoms coming together? Because more number of atoms, more the activity. So that's a single atom chemistry that we do in our lab. Now, the last 10 minutes or 10 to 12 minutes, I try to explain the application of nanomaterials for health. Obviously, this is not our expertise. We do collaborate with the people, the other researcher to explore our material for health application. But as such, I'm not the expert in the field of health. So one of the very recent discovery done by our own institute in India. So this is like one of the Indian discoveries, Sri Chitra Tirunelveli Institute of Medical Science and Technology, where they use magnetic nanoparticle for RNA extraction. Right? One of if you know, when this COVID started, we have to import the RNA kit. Right? How do I detect the coronavirus? You take that sample and break the protein around the RNA and extract the RNA. And based on the RNA, you can tell whether it's a coronavirus or something else. So RNA extraction is one of the key to develop to detect the coronavirus. So this is where this particular discovery clearly explains the application of magnetic nanoparticle. They observe that when you use a magnetic nanoparticle, the RNA binds very strongly and very selectively in presence of exposed magnetic field, and you get a very pure quantity of RNA. In our lab also, we are working on a very different process where we're using DFNS to extract the RNA. Right? You need a magnetic field. That means you're again needing extra energy. Can I extract the RNA without needing any extra energy? So that is something where we already got some interesting result, and we will come out soon in that direction. This is another example, the mask you detect, you want to protect yourself. So this is a mask which has a copper oxide nanoparticle, which again, whenever virus comes there, copper try to disrupt the enzyme structure, the protein structure, and kills the virus. So use of copper oxide nanoparticle is another good example in case of fighting the coronavirus. Important thing that is not studied yet is whether that copper nanoparticle really stable into your mask, or you are also inhaling copper oxide nanoparticle. If that is happening, then it is really dangerous. Nobody really studied the health impact of the nanoparticle when it goes inside your body. So something that pharmaceutical student has to worry about. This is a graphene oxide. So it's not only about the size of the nanoparticle that makes a difference, but here these particular paper shows that how sharp a structure is and how the charge on the surface is, that also matters in deactivating the viruses. So they observe that if you have a single layer structure, if you have more sharper edges, they showed a better antiviral activity, and you need to have a negative charge. When they have a positive charge, it was not active. So it destroyed the virus by this is simple graphene oxide. Another one is the use of carbon dots as an inhibitor for coronavirus, and they prepared the carbon dots using the curcumin, which is the haldi that we all use, and they observe that by using the carbon dots formed from the curcumin, they're able to change the structure of the surface protein, and as soon as you change the structure of surface protein, right, those S protein, and then you destroy the virus, you deactivate the virus. It also suppresses the viral replication, right? So that's another mechanism it works of the coronavirus. You see now, this is 2018 paper. So there are different families of coronavirus. This is not COVID-19, this is other families of the coronavirus. But obviously you can use this knowledge to now develop the material, develop the drugs. Something called nanodeca, which is like, it's a nanoparticle, looks like a coated with say protein or enzymes, and they look like they are more a bioactive material. So the viruses, bacteria misjudge them. They feel like they are one of their own, and then they try to interact, and that's how the nanodecoids kill these viruses. That's very unique technique that is available using the field of using the concept of nanomaterials. Recent work where they use functional carbon quantum dots to again inactivate the virus. They observe that when you have a carbon dots functionalized with this boric acid, organic molecule having a boric acid at the surface, so 4-aminophenyl boronic acid. So they were able to selectively bind and inhibit the virus, coronavirus. This is another one where they observe that when you take this HR1 peptide inhibitor and put it on the gold nanorod, then it shows better inhibitor property than by itself. Ideally, the peptide itself is an inhibitor, but when you put it on a gold nanoparticle, maybe they are properly oriented, properly dispersed, so you get a better activity, a better inhibitory effect. So that's some sort of a support to already existing inhibitory property of the peptide. And if you want to know more, there's this nice review which tells you what are the other possible ways of treating the COVID-19 using the nanoparticle. In addition to this, our material is also used for drug delivery. The DFNS is used for the drug delivery. So I'm going to, in the last 5 minutes, I'm going to explain you more about the use of nanoparticles for drug delivery and other applications. So this is one of the, this is again a DFNS, which was then functionalized with say amino group, because I told you DFNS is silica as so you convert that OH into amine, and now you can load say DNA or RNA and then selectively release at particular site. So this is more some sort of a, this spherical fibrous ball becomes your drug carrier, and you know it has high surface area, high porosity, so you can load lots of drug molecules, and for drug molecule to also release is more efficient. One of the example. This is another example where this particular drug was loaded onto the silica, and they observed that the loading was more efficient, the delivery efficiency was better, and drug was also stable for up to 5 days. So there are several advantages of using the nanoparticles to release the drug, load and drug. There's also a good example of Ayurvedic drug delivery. Curcumin-based curcumin coming from the turmeric, which is something that we are using. That is the Indian community is using from 2000 BC, and this is something Ayurveda also recommended, and obviously most of us use it regularly. So this particular Ayurvedic drug, curcumin, was also able to they able to load large number of curcumin on the DFNS, and they were able to do a drug delivery to breast cancer cells more efficiently than curcumin by itself. Then there is something called a photothermal ablation therapy, where you release the drug as well as you can also provide generate isolated heat which kills the cell. So here they coated the DFNS with this particular molecule called polypyrrole, which has ability to harvest the near IR radiation. So this DFNS coated with the polypyrrole captures the near IR, and then that produces lots of heat, and that heat isolated, say near the cancer cell or some infected cell will kill that cell. So that's a photothermal, and so you can have a better photothermal therapy using the nanoparticles. Where you can tune which light you want to harvest and amount of heat that you want to produce. The black gold is another example where I can take that black gold, expose with light, create a heat. So I can also use black gold for photothermal ablation therapy. That is something we're thinking of. So this is another example where not only the chemo but radiotherapeutics can also be used to also be delivered using the DFNS. So this is the platinum drug. As well as holmium complex 165HA. So this is a combination of chemo and radiotherapy, and they observe that there can be controlled release of the drug from the DFNS for up to 40 hours. So you can have a very slow and controlled release of drug at one particular point, and which can be activated by neutron activation. Not only the drug delivery, the ELISA test that is one of the most important tests that we do to study antibodies, to detect antibodies. So they observe that you use a DFNS, then the sensitivity of these detection systems is increased by 2,000 times. This is a dramatic increase in the sensitivity by simply putting those antibodies and first and second antibodies onto the DFNS rather than using it direct, because now the accessibility is more and you get a better sensitivity. So even a small amount of antibodies can be detected by the DFNS based ELISA plus immunosorbent assay technique. Right. So with that, I like to conclude that nanotechnology can help to tackle the challenges of energy and environment. The combination is the climate, right, and the health, which is something which is more interested for you guys because you are from pharmaceutical industry. So I give you a brief account of how the nanotechnology or nanoscience can help us to fight these challenges that human is facing right now. With that, I like to thank my group. I and my team, Rajesh Gaigamwar, Rishi Verma, Sushma Punju, Sushma Raul, a very small group. In TIFR, we always have a very few students so that we can have a proper close interaction rather than creating a factory of PhD students, unlike other institutes. And our institute is 75-year-old. We are celebrating 75th year here. In our international fundamental research, we do science in chemistry, various branches of physics, maths, computer science, and biological sciences. So all fundamental research, and you now must have realized if you want to solve the climate change problem, you really need a fundamental discovery where I am able to capture and convert CO2 to methane or methanol using sunlight at room temperature with a productivity that makes the process commercially viable. And this is only possible if I have some fundamental discovery where I design a catalyst which can really do that. Without that, it's not possible. So obviously the fundamental research is the key to fight a battle with the climate change. I'd like to thank the Department of Atomic Energy, the CEFIFRA, the Shell Mission Innovation for funding our research group. With that, I'd like to thank you all for listening to me. And I'm open to take the questions now.
Thank you, Vivek. And it was really a great insight for me, and I hope for all audience, in moving our therapeutics, pharmaceutical sciences into the fundamentals of some of the materials, advanced materials, in actually taking world's biggest dream, converting, the gases. I think that's a larger dream, not for individual, but I think whole world is dreaming, right? And you have been very you have been anticipating that probably will have to have solutions soon before it's very late, isn't it? So it's really great to hear you, not only the talk, but see to overall have a review of all your publications over the year. So I have 2 to 3 general questions before there are questions actually emerging at the chat site. If you could also look over there. We'll take actually very specific questions rather than the general questions. But let me ask general question as a liberty as a moderator over there. I have a question, like typically when you publish a paper in enzymatic chemistry or PNAs or nature protocols, right? These are probably three latest highlights what you did it.
Yeah.
What is the thought process? How does the work actually build? How does students actually add up to your thoughts? And typically, how many years it takes you to make one paper like PNS, quoting PNS as one of an exemplary outcome there? So that's my general first question, because there are many students here, and they would actually, all of us would like to dream, follow your path of publication. So I would like you to deliberate something on that line.
Okay, maybe, yeah. So the publishing is always a challenge, and publishing in a bigger journal is always a challenge. So the very first need is a new idea that is not published in the paper. So something, because it's extremely competitive field. There are maybe thousands of people are working in this field, and if you go to China, United States, they are well equipped to do the thing in a faster way. So if you want to compete with them, the only way or the best way is to come up with an idea which is very unique, which they also never thought about. Once you have the idea, then it's the implementation. How do I plan the experiment to so I have idea means your hypothesis. So I will do this and it will happen, right? Based on obviously your experience and your knowledge in the field, and then experimental planning to prove that that is really happening. And obviously you need lots of infrastructure to do a different kinds of experiment. If you don't have the infrastructure, one can collaborate. We also collaborate, right? Even in TIFR, you can see most of our work, we need a collaboration, because you can't do one person cannot do everything, right? I want to do a solution NMR. I'm not expert in solution NMR. I want to do a DFT calculation. I cannot do a DFT calculation. So rather than having that narrow-minded approach, be open, be collaborate. That's the second part. First part is the idea. Another important thing that you said, Jayant, is about the student. What is the role of a student? For me, student is the key. They are the key role. Obviously, we have a very extremely talented student, but it's not about the talent. It's also about how the faculty and student interact. If you come to TIFR, you will see that you will not able to differentiate who is student or who is faculty. We are like brothers. We are like a best friends. We speak, we argue, we disagree, we fight, we do every single thing to make sure that our science is good, our idea is correct, our experiments are good. So because the students come with a fresher ideas, whenever you become a faculty or a scientist, you get some sort of inertia of thinking, or you think in one direction. So you obviously come up with idea, but students also come up with their own idea. Then we have lots of interaction, discussion, and that helps us to really strengthen our ideas and come up with a newer experiment. One is having the idea. One can think of some crazy thing, but then you have to prove that idea, right? For that you have to come up with a very unique experimental design, right? Design to make a new material, design to make new functionalization. How do I characterize? So all of these, if one do it very systematically, there is always a possibility of having a good publication. Obviously, it's challenging in India because in addition to the science, there is always other things that plays a role in the field of unfortunately in the field of publication. But one has to ignore that, because that is something now in our hand, and just do a good science and try to write a good paper.
Thank you. And so you also mentioned about this translation of CO2 absorption and that recycling it, right? So what stage it is? Is some company actually translating this proof of principle, or?
Ideally, no, we can approach the company, but what I said is all of these is good at the basic science level, but for a company to take this to the next level, what they will look the amount of methane produced is cheaper than the methane I'm getting from Saudi Arabia or some other country, right? Because you're not going to put 1,000 rupees to buy 1 liter of gas when you get it in 75 rupees, right? So science is there, but the productivity is low. It's really low. So that's where you need a breakthrough in the field of catalysis, where I can do that same science with a large number of methane products, large number of methanol products. The productivity is still not there. So I don't think at this stage we will, at least our research will go that stage.
So my question is, how much amount of a catalyst that you actually make, or non-catalyst nano substance which actually show this? So what is the size, mass, volume that actually you make in lab?
No, that's the upscaling question that you are asking. Upscaling is possible. I told you that the way we make the material is very simple solution-based technique.
Right.
And we intentionally use that technique because because if you cannot upscale, there's no point in making the material. It will be just a publication and you end there. We already showed that when we discovered the material, it was in a milligram scale, but now in the small lab, in a 2-liter reactor, small round bottom flask, get up to 32 grams of the silica. So that's the big thing to come from milligram to 32 gram. Now anyone can take it to a larger scale, to pilot plant scale and a higher scale. So making the material is not a problem. But now it's the property of the material itself is not that magical that is required to make a commercially viable process in terms of the productivity of the methane or a methanol.
So good. Thank you very much. We have few questions which I am going to select and pass it to you very selectively, because you mentioned about you have to have a selectivity. So we'll not take actually general questions for the interest of time. We have here Dr. Shashwat Banerjee, and he has been following your research and we have been citing you. So few of the citations or many of the citations what you see must be acknowledged to Dr. Shashwat Banerjee. So Shashwat, do you want to ask your question which you typed there? Please unmute and ask the question.
Yeah, sure. A very good presentation, Dr. Polshettiwar. My query for you is, since the nanoparticle that you had synthesized is fibrous in nature in the outer part, so is this nanoparticle has some special property, like can it enter the cell while drug delivery in a better way as compared to other nanoparticles, say spherical nanoparticles without fibrous tentacles on their surface? Have you seen this new features or new characteristic?
Okay, so that's a very interesting question. What is obviously this is not what we study. This is most of the time a collaborative work. What we observe as in comparison with the solid sphere is the loading of the drug, right? Because now it has open high surface area structure, you can load more drug. But this is a very interesting question, whether the penetration into the cell is more efficient because I have the fibrous structure over the solid sphere. That is something I don't think people have studied yet. One should do that study in a very systematic way. Loading is better, but the penetration into the cell.
We have a question from Dr. Ashwin.
Hello.
Ashwin has a question. Dr. Ashwin has a question. Ashwin, please.
Yes, sir. Yes, thank you, sir. It was a good presentation, Vivek, sir. And I have a question with respect to your discussion where we are discussed related to copper oxide, which helps in inactivation of the coronavirus. So my question was, what might be the probable mechanism of copper oxide that inactivates the coronavirus?
Okay, so I think I showed you the few lines where they said that somehow copper oxide deactivates the surface protein. So it interacts with the surface protein so it's some sort of a chemist option, I guess. And once you have a interaction, its structure is so some sort of a defolding or unfolding. And once the protein structure is unfolded, you expose the RNA and ideally deactivate the virus. That's the only information that is available in the literature.
Okay, sir. Thank you, sir. Thank you.
Professor Chaudhary, VP Chaudhary has a question. VP, are you there? So I'll read out the question if he's on a mute mode. So Vivek, he asked that if he wished to actually coat a small nanoparticle onto a large particle like 500 micron, one particle to other particle, is it possible? And how do you want to commit?
Yeah. So you don't want to use the word coating. You want to use the word loading. That's what we do. We take a 500 nanometer size silica particle, and then you load say 1 nanometer, 2 nanometer, whatever the size of the nanoparticle you want, and you load them completely. In fact, you can reach a stage where you fill entire surface by loading these particles, and there you can also call it as a coating. But if you coat, then you lose the surface area. So you don't want to coat, you want to just load the nanoparticles. You can even load the single atoms onto the surface. So that is something that we do regularly. And that's called the heterogeneous catalyst, right? You have bigger particle over, and then you load the smaller particle as active site.
This
Possibly
catalyst okay, please go ahead.
Hello. Is it possible in our simple laboratory like in our college? Hello, Vivek.
Yes, it's very much possible. In fact, we published a paper recently in Nature Protocol where that was the objective, that every single person who has a round bottom flask and a heater and a magnetic stirrer, even you don't have a magnetic stirrer or mechanical stirrer, can make it. And we even gave the video. There is videos on YouTube where every single step was given in every detail, so that that was the objective, that everyone can make it. And it's
So
very
Nature
easy.
Protocol paper must be reviewed, right? Nature Protocol must be read. I think that's an open source, so it can be.
Yeah, it's open source, and the video is obviously also open source. Yeah.
So we have here Vivek.
Thank you.
Right. So Vivek, we have here Kale. Anup, you have a question? No.
Yeah. The question.
Satish, I hope today you don't have a question.
Yes, sir.
Go ahead.
Yes. Really nice presentation, Dr. Polshettiwar. The one question I have is apart from the gold nanoparticles you talked about, the spacing of the gold nanoparticles to create that defined effect of surface plasmon resonance and like local heating, what you said there. So what are the other methods that can be used in tuning the size spacing between the gold nanoparticles? Because that is very interesting aspect and it has a lot of applications in various fields.
Yes. So that's very good question. So see, that's what I said. It's if you really think about changing the distances, nothing comes in your mind, right? How do I change the distances? I can change size, shape, morphology. So after long deliberation, we thought, okay, this is the way that we know. I don't know. There is no way in the literature also. I don't think there is any other way I change the. There is a one way where you put a gold particle with a linkers and you change the length of the linker. But then the problem is when I expose with light, these linkers will get degraded, right? And then the nanoparticle will stick with each other. So the linker thing will not work. That was known in the literature. So that's why we came up with this process of controlled nucleation and growth. And I don't really know if there is any other way of doing this. But this process can be used for all the metals. It doesn't need to be for gold, but you can use it for almost all the nanoparticles.
Correct. The one way we did recently is we use graphene oxide or graphene sheets as the template for spacing these nanoparticles. As you rightly said, like nucleating them on the graphene by taking advantage of the graphene as a template and the groupings there like hydroxyl groups and other groups. So that is unpublished data, but that approach is.
See, Anup, Dr. Anup, that will only be the first step. That's what we did. If you look at the way this is done, the first step is silica having a OH and you put it. But how do I control the distances? One is like putting the gold onto the surface, having a different concentration will give you a different loading and different distances possibly randomly. But how can I systematically reduce the distances? Right. So once you load the gold nanoparticle onto the graphene, and now I want to bring them more closer. How do we do it? So that's the question.
Right. Yes. Thank you.
So Professor Sangve has a question or a comment. You want to unmute the mic, Dr. Preeti? So she asked about on a comment, you to be commenting about these kind of nanoparticles, if they are released in environment, will they themselves have some additional burden? That's a question she asked me.
Yes. Yeah. That's one of the most important questions that she asked, and this is something not really well studied. That what will happen if the nanoparticle goes into the environment? Not what will happen when you inhale the nanoparticle. That's what I said. People are using copper oxide into your mask. And if you are protecting from virus, but if inhaling the copper oxide nanoparticle by itself, it's a problem, I guess. So those studies need to be carried out. And that's why one of the ways is you use a bigger nanoparticle, right? Then the possibility of inhaling or flying in the environment will be less, and then load the smaller active site onto the bigger nanoparticle. You still get the good activity, but somehow they are more stable and more safe. That's one way to go.
So maybe before somebody have another question, Vivek, I want you to comment on the area which you have actually been working for a long time. So can you give us an idea about actually where this area has been implemented, and say maybe as a catalyst or heterogeneous or non-heterogeneous system or homogeneous system, where these kind of catalysts have been widely being used in?
In most of the industries, the petrochemical industry, polymer industry, it's a heterogeneous catalyst that people use, right? The platinum-based, palladium-based, even in the pharmaceutical industry, most of the catalysts are palladium-based, Suzuki coupling, Groves catalyst. So they are used everywhere. Now what they are looking for is, can I convert those heterogeneous catalysts into some sort of a heterogeneous nano catalyst so that I can do the same process in a cheaper way, more efficient way? At the end, industry wants to do this, save the money and get more productivity, right? So they are used everywhere. They have a huge application in almost every single field related to the chemistry. Obviously, our goal is not only for those classical catalysis, but we also want to really develop a CO2 based chemistry, right? You get most of these hydrocarbons, something from this.
From Grubbs catalyst, which actually transform. No. Maybe let me put this question like that. Yes, we know that catalysts have been widely used in chemical synthesis and hydrogenations and petrochemical industry. So from Grubbs catalyst to, so I want to ask, that's a past. So what's the current and future materials like what you actually have been designing?
Okay. So the future, maybe I'm a bit biased, but future is all about, can I use CO2 as my feedstock? Not the fossil fuel, not the carbon, the alkanes and alkynes and the oils and everything that you get from the well. So can I use CO2? So CO2 based refinery, I get all the petrols, hydrocarbons, chemicals from the CO2. That is something not done. That there's no single process where it is used in industry. So that's the dream. That's the dream project that we and lots of other people want to do. And that is require a breakthrough in the field of catalysis, which can be done using the nanomaterials and nanotechnology.
So there's the last question, I think, in the interest of time, that can virus and bacteria be entrapped? I think we spoke about copper oxide and other chelations kind of components, but can you also absorb them, these bacteria and viruses? Probably that's a comment that somebody has asked in the end.
Yes. So in fact, that's something people haven't tried much, because there could be a selectivity issue between the nanoparticles. But recently, I am not an expert again in these bacteria viruses, but then whatever the basis I know, and then the knowledge in the nano, I recently put a Facebook post where I said, okay, you look at the DFNS and look at the coronavirus, they look very similar. So can there be a science where the virus try to attract with a similar looking nanoparticle? Something like that. That's a very different science that is not really tested yet, but that could be one of the things where virus get confused whether that other nanoparticle which looks like a virus is a virus or something else, and can that be a way to trap and kill deactivate the virus? That could be very interesting.
Like molecular imprinting, there was an era when actually molecular imprinting was very well practiced in polymer chemistry. So with this specificity.
Yeah.
So Satish, I will before I give my vote of thanks and before you come to your vote of thanks, Satish, any question? Yes. Satish is surprisingly not asking question today, Vivek.
No, I let others ask.
Okay. So Satish, I think my vote of thanks here before you do it and invite Kuchekar sir. So Vivek, thank you very much, and I also thank Satish to interface this today's talk. And I took over the moderation actually, for some reason. So Satish, I blame you for my Saturday, plans little dismals there. But it has been pleasure, and seeing Vivek, making that possibility to actually interact with Vivek over 1 hour. And thank you, Vivek, from my side. I hand over to Satish and our Dean, Dr. B.S. Kuchekar, to speak to you and express their thanks.
Sir, thank you. Thank you. Indeed, it's a great pleasure to listen the great scientist, my brother. Really, I am very feeling proud and extremely happy to propose my vote of thanks on behalf of MIT World Peace University, School of Pharmacy, entire management team, EP sir, our Vice Chancellor sir, Pro Vice Chancellor sir, our Dean beloved Dr. B.S. Kuchekar sir, and our HOS Dr. Baheti sir, our friend, our guru mentor Dr. Jayant Khandare sir. Because of that, this event could make it successful. because of his busy schedule, we really could make it because of Jayant sir only. I really thanks to once again Jayant sir for taking this initiative and making this platform available for all the students to learn about the nanotechnology. Really, it's a brainstorming and informative, effective, I could say, session to one and all. I once again and extend my sincere thanks to Dr. Vivek for your busy. You could make this event and webinar successful, and really it was very informative to one and all. I hope all participants are enjoyed with all their queries have been solved. If any information, any help required from my brother, I really assured on behalf of my brother, he will be really available for any technical help, any collaborative work. We are also looking forward to him as our mentor for MITWPU for bringing a new avenues in nanomedicines, nanotechnology for his materials. Once again, I thanks to our technical team, Pankaj and Vishal sir, for making this, all technical help and all these things. Once again, I thanks to special thanks to Jayant sir because he has really wonderful job since last 1 week. We have been seen. He has made many things available to us to learn many things. Thank you once again to one and all. Over to our Dean, Dr. B.S. Kuchekar, sir.
Hello, Dr. Vivek Polshettiwar, sir. Thank you. Thank you so much on behalf of MIT World Peace University for very meaningful, interesting, interactive, and informative session, sir. Thank you. Thank you so much.
So with this, with this, allow Vivek to say goodbye here, and you must take care. I hope TIFR is fully active and you are already in the office. Nonetheless, actually, you are very protective institute and very isolated. And although you are close to actually Navy Nagar and other places, so stay safe and let us hope that we all go to the offices very soon. Thank you, and let us switch off this meeting and have a great day ahead, Vivek, and all of the joinees.
Yeah. Thank you once again. Thank you, Satish, and thank you everyone. Bye bye.
Yeah, thank you. Bye.